about DNS security. So, just a few sentences to myself. My name is Johannes Weber. I'm working as a network security consultant for a German company called SVA, System Vertrieb Alexander GmbH. And I'm primarily focusing on projects within the network security area, that is firewalls. So I'm working primarily with Palo Alto Network firewalls, also little FortiGates. And I'm focused on two technology topics that are DNS and IPv6. So those are not directly firewall related, but network related. However, I'm trying to solve different problems and doing some secure concepts for our customer bases. If you want to connect with me, I'm a LinkedIn user and I have a blog called weberblog.net where I'm blogging like once a month about topics around Palo Alto, IPv6, DNS, and so on. So what's the agenda for the next hour? 2 years ago, I gave a talk about DNS. We know it's always DNS, as we have seen with Saka's presentation as well. It's always DNS. This time it's about DNS. And yeah, it's I want to talk about DNS security and how malware uses DNS and what you can do on a defense from a defense perspective. So we want to look at malicious DNS, different topics like malware, lookalike domains, DJAs, DNS exfiltration, DNS tunneling, DNS spoofing, all such buzzwords. We want to have a look at DNSSEC. Spoiler, DNSSEC is not the same as DNS security. So DNSSEC is just a small portion of DNS security. Yes, DNSSEC is named the DNS security extensions, but when we talk about DNS security at all, it's way more than just DNSSEC. We'll have a look at dot and do. Yeah, I will show you some attacks and defenses and some tools. Normally, this is like a one-day course. So I will only spot on the tip of the iceberg, and hopefully you're not confused, but you get the idea of how this DNS stuff works. Okay, so that we are all on the same page, when we're talking about mere DNS, this is really from a high point of view, this is how DNS works. So I hope everyone is familiar with this. I'm searching for my... So normally you have something like a client. That is, you have an application, let's say a browser. The browser types in mybank.com. The browser sends this DNS query to the stub resolver of the operating system. The operating system sends a recursive query to your resolver or your recursive DNS server. So the first point to note, I'm not talking about the DNS server solely, but I'm always talking about the recursive DNS resolver. This is the guy who does the work for you, because this one now walks through the DNS tree, starting by the root to the top-level domain, to the domain. Maybe you have some different name delegations. This guy now, we have these arrows, queries for iterative DNS queries to the authoritative name server. So again, this is not only the DNS server, but it's the authoritative name server. We have a couple of them, so there would be many more communications here, but in the end, your resolver returns the one and only complete answer with a CNAME and some additional records. In the end, the stub resolver on the client will get an answer. Mostly it's for the A or the quad A record, but you also can query for text records and so on. So this is the basic DNS. I hope everyone is familiar with this. First remark, if you care about privacy, think about using your own recursive resolvers. So I'm not talking about home networks, I'm mostly talking about enterprise networks, because this is where I'm working with. Right? So as an enterprise, don't use 8.8.8.8 at all. Why? Yes, it works, it's highly available, it's fast, and it's easy for you to configure, but the guys from Google, for example, they are not operating 8.8.8 because they are nice persons, but they are operating it because they want to get your data. So if you're using an open recursive resolver, just be aware that 100% of your DNS queries is seen by the resolver. So if you're an enterprise, please consider implementing your own or using your own recursive resolver so that no one else gets your data where your clients or where your users are surfing to. Okay, let's go to the interesting part. Let's go to malware and DNS. How is malware using DNS for its purposes? On a very basic view, please consider that you have some kind of malware on your computer. And now what is a malware doing? Basically, it wants to check whether it has to do something. Consider like a botnet. So we have command and control traffic. So this is nothing interesting from a DNS perspective because it's the normal DNS. Your malware will ask for something like download.malware.com. Your recursive resolver will get the answer, and it will get the answer back to the malware. So what's the problem here, or what's interesting? The interesting part is that there are stats that 90% of all malwares out there are using DNS at a certain point of their cyberkill chain. So that is, for us as the security guys, it's quite easy to fight against them. How can we do this? We can do this if on the recursive resolver we implement something like DNS feeds or block list or based on reputation something. So what is this? There are lists out there. You can purchase them, some are for free. You have to find your situation, how you would use it. But in the end, consider a list of known bad host names. And this list has many million entries, and this list resides on your recursive resolver within your company. So now, if a DNS client, in fact, it's a malware that's already within your network, wants to connect to a command and control network, he wants to a botnet, to the server, to the command and control server, this malware will first query for the DNS record of this server, and now your recursive resolver can actually respond with an annex domain. So this is quite easy. Doing this, you only have to use this DNS security feature on your resolver, and you're securing your whole company. Because independent of where your clients are in your company, in your rooted infrastructure, all are using the same recursive resolver, don't they? So by securing the responses from the recursive resolver, you have already secured many internal clients because the malware is not able to connect to the botnet server again because the annex domain, because it does not know to which IP address it should connect. So 90% of malwares use DNS, for example, to find HTTPS servers to download executables, command and control traffic, or a kill switch. Maybe you've heard of a kill switch, some malwares doing a DNS lookup, whether or not they should operate or they should start something or they should be killed by themselves because they are afraid of being detected and so on. So this is all done via DNS. What's the defense? Known malicious feeds or DNS block lists. There are various names. In the end, you will have a component on your resolver or on your intermediate firewall, I will come back to this, that blocks those DNS queries, but not only blocks them, but sends back an annex domain. So from the client perspective, you will see a valid DNS response, but with an annex domain or with a sinkhole address. A sinkhole address is an idea where your DNS, your recursive resolver, would not simply send an annex domain, but it will send back an IP address that is known to you. For example, 10.6.6.6, for example. What's the reason for this? When this client, when the malicious malware now tries to connect to the command and control server, it tries to connect to the IP address 10.6.6.6, and now you can have firewall rules where you have a rule at the very top of your firewall rule set. If someone ever within your network connects to this sinkhole address of 10.6.6.6, for example, you will get an alert because you know there's something wrong, because this IP address is never used within your company at all, only when the DNS sinkhole was answered. You got a question, Sake? Okay. The next part is not used by malwares, but it's used by phishing mails to trick the human brain. It's called lookalike domains. There's 2 times the name PayPal, correct? Well, unfortunately not. I've printed it in another font. The first one is PayPal, as you know it. The second one is PayPal, with an uppercase I. So what's the problem in here? If an attacker tries to fool you, he sends you a phishing mail, and he wants your credentials, for example. He wants you to click on a link to be redirected to the attacker's malware site. But he does not own paypal.com, and it's probably hard to spoof DNS. But he has made a trick of this lookalike domain. So within this phishing email, he will make the font in the first way so that you think you click at paypal.com, while in fact you're clicking to something else. So the attacker beforehand has registered this PayPal domain, of course. He has made the A records, he has rebuilt the HTTPS server looking like PayPal. And when you receive the phishing mail and you click on this link, you have almost no idea that you're on the wrong site just because of this lookalike domains. Yet another example, Gmail. So, you know, the human brain is capable of reading words even though the letters are in the wrong direction, in the wrong order, but you still see them in the name. So this attack feature is called lookalike domains. Again, it's not about attacking DNS, it's the normal DNS, but it uses the human brain to fool us humans. So again, what is a countermeasure? The countermeasure is exactly the same as we saw before, because you will have DNS lists with all those bad lookalike domains. So there are DNS security companies out there, or the firewall brands, we already talked about the firewall brands, that have these lists of lookalike domains in order to secure their clients. So because when you are within your company, you click on a phishing mail that redirects you to PayPal, the recursive resolver is capable of blocking this DNS query or sending back an NX domain or sinkhole address. So it's the same concept. I've not explained one word. This is RPZ. So when you're operating a complete normal DNS server like Bind has this concept of an RPZ. This is called response policy zone. This is a type of DNS zone that is meant to have this DNS block list feeds. So you can purchase these RPZ zones. You're buying them on a security company, DNS security, and then you can implement them on your normal DNS server that has this feature. This is what RPZs are meant for. Next one. So the attackers are quite smart. So the attackers know, there are these lists of known bad host names, as we have already seen. So the attacker, the malware on your computer now tries to connect to their malware site, and he knows, well, my names are all within a list of bad domain names. So what can the malware do? The malware uses something called domain generation algorithms. Consider it like a random password. So there's this DGA that sits on the malware, and the same DGA algorithm that the attacker knows. So let's say that the malware sleeps for 60 days. And one day, at day 60, the attacker knows which domain-generated algorithm the malware will use tomorrow. So he registers this random domain, knowing that the malware, who is using the same domain generation algorithm, will use this random domain name at the day 61. So what's the problem here? Our idea of using DNS block lists is not feasible anymore, because we simply have too many DNS names, host names, that would be in this list. Even worse, you can do it with the dictionary-based names. So you probably have heard that you can generate a password or a passphrase, where a passphrase has like 5 words out of the dictionary, and it's even more secure. So in fact, these two host names I generated last week, they are online passphrase generators. Just give me 3 random names out of a dictionary, something like packageflyaccept.com. When you're looking at the first pseudo-random names, you might have a clue that it's not that it's kind of suspicious. But when you look at the lower names, you wouldn't expect something suspicious. So, in fact, DNS block lists are not working for this kind of attack because they are simply way too many. In fact, millions of domains are registered per day. So the concept of listing all of them and have them at your recursive resolver is not feasible anymore. Most of them are malicious. So we have to do something different. From now starting, we are assuming that all new domains are malicious until we have verified that they are not. So the concept for blocking this type of attacks is we have some feeds that are named, for example, newly registered domains or newly observed domains. That is, when you're doing a DNS lookup, when your malware is doing a DNS lookup, and you have this DNS security feature on your resolver or on your firewall, you will land within a DNS category of newly observed domains, and you can set this category to block. Because just within the first few days a new domain is registered, we consider them to be malicious. So this is how a defense for this attack works. Again, you have to implement this feature on your recursive resolver. For example, Infoblox is a well-known brand for DNS servers and DNS security, or within your firewalls. Next one. The next one is DNS exfiltration. So now we are using, again, the simple DNS system. Let's consider you have a malicious malware on your client, and you want to get some data out of the company. What would you normally do? You would do an HTTPS upload to OneDrive, for example. You have this file where you have this interesting stats, and you want to exfiltrate this file. What's the problem when you're as an attacker, what's the problem when you're uploading this file through OneDrive through an HTTPS channel? Well, most of the firewalls are doing, in an enterprise network, are doing TLS interception, or they have something like like threat prevention that looks into the uploaded files or blocks uploaded files at all. So as an attacker, you're not able to upload a file through a TLS channel because it's blocked somewhere. Not so for DNS, because DNS is you're flying under the radar. Because that you're using DNS, you have to use DNS for your normal work, don't you? So DNS is quite normal traffic, and it's just getting the names, isn't it? Well, unfortunately not. You can use the DNS exfiltration. So this is just a really kind of a stupid example, but please consider the following. The attacker has the domain attack.biz on his own authoritative DNS server. If his malicious malware on the computer asks something like password is ABCDE, because ABCDE is the information that the attacker wants to exfiltrate from the company. You're still reusing the recursive resolver, and the recursive resolver does what it should do because it asked this query to the attacker. So what's the problem here? The problem is that the attacks we already saw, the recursive resolver has blocked the answer with an NX domain to the client. But here, it's not about blocking the answer that we know is malicious, but we should already block the outgoing initial query. In fact, this attack has no answer at all. Whether or not the authoritative name server from the attacker is answering or not, I don't care. I already exfiltrated some kind of data. In fact, there are tools out there that do this for you. So you can give this tool a file of size 1 megabyte. You can operate this tool with a password. The tool will slice your file into several small chunks. It will encode it, it will decrypt it. It will send DNS queries like 1 query a minute. So it's really low traffic. But after 1 day at the authoritative DNS server of the attacker, you can decode and decrypt this whole file. So by just using DNS, you have brought some data out of the company. So it's really hard for these attacks to be detected. I will skip the live demo in case we have some time left. The next one is now called DNS tunneling. So DNS tunneling is the techniques, and this is probably the most coolest thing I've ever seen when I've seen it for the first time. So here, it's about a two-way communication. The client wants to communicate with the authoritative DNS server. The malicious malware wants to communicate with its command and control server. But this time, DNS is not used to simply resolve the domain name and get an IP address back. But DNS itself is used for the tunnel mechanism. That is, the software on the client, for example, asks something like myhiddenquestion.attack.biz for a text record, normal DNS. The attacker who has this authoritative DNS server can say, okay, you're asking for my hidden question attack.biz, the text record, and the text record is rm-rf/. And the client will get this answer back. So this is not that the attacker and his authoritative name server is operating a zone file where you're updating some host names once a week. But it's like a script, it's like a huge software. He can make decisions. So whether or not the client is asking something, he will have a logic and will reply yes or no or some commands, whatever. Even more interesting, you can, here are some tools that you can use for testing purposes, of course, only. For example, DNS exfiltration or DNS tunneling. There's this tool called Iodine. This tool is quite interesting. Why? Using Iodine, you are really tunneling an IP traffic through DNS. Well, think about this. Iodine, you have a server component and you have a client component. This is the listing from the client component. So as you can see here, I started Iodine with a passphrase. So because I want to encrypt my tunnel, it's really like a VPN tunnel. Yeah, you're using the recursive resolver and you're using a domain name that is delegated under the attacker's domain name. So my test domain is weberlat.net. I used this io.weberlat.net, set the NS records pointing to the server for this Iodine. So what this Iodine does, it uses an IP address for the DNS tunnel interface. Wow. So this tool adds a tunnel interface. It's a real network tunnel interface with an IP address and a route. It auto-probes for the max MTU size, like 865.4 is okay. Connection complete, transmitting data. So using this DNS tunneling technique, you have a two-way communication. You have an IP tunneling mechanism that still uses DNS. And more interestingly, it does not use a client to the server connection directly through a firewall, but it uses the client asking the recursive resolver within your company network. The resolver asks the iterative DNS query to the authoritative name server, which is the server component of Iodine, and so back. So the round trip time is quite high. We are talking about seconds. But I don't care. In the end, I can use this tunneling as a full IP tunnel through the usage of DNS packets. When you're looking with Wireshark at this, it basically tells you it's DNS, because it is DNS. So I have a coloring rule. My DNS packets are always colored in yellow. So you can see something like, yellow on yellow is not that good. You will have something like random data, and you will have something like random answers. But this is actually IP traffic within DNS packets. So this is really cool, from an attacker's point of view. There are malwares out there that are using this. It's not 90%, but at least be aware of this type of attack. How would a defense technology look like? Because we can't use everything we have seen so far. We can't use DNS block lists because these host names are generated on the fly. So we need a different approach. The different approach here is called deep query inspection or some other fancy word. I refer to deep, it's not deep packet inspection, but it's deep query inspection. What are we doing here? For example, we are analyzing the length of the labels of the host names for DNS, or we are doing a lexical analysis. That is, in the real world, DNS records are always like www or server or mail or something. So if we have random looking DNS names, there's probably something wrong, but it's just one out of many indicators. Or we can look at the frequency. Do we have 10,000 of same-looking random DNS queries to the same for the same domain or not? So these are possibilities to analyze such DNS exfiltration and DNS tunneling events. What's the problem here? The problem here is that this requires memory. Your intermediate firewall can't do this because your intermediate firewall might have some DNS block lists, and it can have this 1 million entries for a DNS block list, but it cannot do this deep query inspection. Why? Because, let's say, over a time period of 1 hour, it has to store every single DNS query to do this analysis, and your firewall is not meant to store so many packets. So this can either be done on a recursive resolver, or on a firewall that uses some cloud delivery, something application thread, you name it, license, then it's still possible. So this brings me to this question: where do I want to leverage DNS security? When we are on an on-premise network, you probably will have something like this. You have one single perimeter firewall, which is probably capable of DNS security. And you have your recursive resolver, while within your internal network, you're only routing. So when you have this, you can think of maybe you want to leverage DNS security on your resolver. Why? Because on your resolver, you can see the source IP addresses of your clients. If you would use DNS security on this perimeter firewall here, which source IP address for every DNS query will you see? Only the source IP address of this resolver. So doing some stats, or if the security guy wants to know which client has this malware installed, it's not easy to answer in the first scenario. If you have not only a perimeter firewall, but also a segmentation firewall, you can think of, or you can suppose, using your DNS security on this segmentation firewall, because there you can see every single DNS query completely. There are still way more questions. For example, do you have the license for the segmentation firewall? So for example, in the real world, if customers have a segmentation firewall with lots of throughput and a perimeter firewall with less throughput, but it's cheaper to license the DNS security feature, for example. So I'm talking about these big vendors like Palo Alto Networks, FortiGate, Checkpoint. Yeah. So it's maybe a license thing where you want to leverage DNS security. Or you want to ask, do you want to use the cloud or not? As I said already, this DNS tunneling, DNS exfiltration, the best part to leverage this DNS security is the resolver, because the firewall can't do it. The firewall can do it if it uses a cloud, but maybe you are within an air-gapped network, or you have the requirement that you're not using the cloud services for everything, so you're only using on-premise network. So the question where to use your DNS security, it depends. You have different methods. It even gets worse when you are considering the road warriors. So if you are within your home office, and you have installed DNS security on your resolver and on your segmentation firewall, but your client will use some kind of open resolver when he is at his home office. What are you doing then? Well, the answer is you will use something like a secure DNS resolver. This is part of the SASE SSE stuff. So for example, you can use an agent on the client itself, where the DNS queries are redirected to a secure resolver from company X, where you have license Y and policies Z and so on. Or you can use a full tunnel, a full VPN tunnel, a real VPN tunnel, not a DNS tunnel, back to your company in order to use your on-premises DNS security stuff. Okay, so what I wanted to say is when you are leveraging this DNS security, you have to consider where you are placing your components and where are your users that you want to secure. We're coming to a next topic. It's called DNS spoofing. So up to now, we only use DNS as it's meant to be. The attacker has an authoritative name server, the client has a malware, but it uses the DNS as it's meant to be. So now we want to go a thread further. We want to spoof DNS queries. So what is DNS spoofing? DNS is based on UDP port 53. Mostly, sometimes we have TCP port 53, but really the way more than 90% are UDP port 53. What's the problem with that? It's stateless and it has no security at all. So when you are an attacker and you are capable of doing a man-in-the-middle attack at layer 3, it's no problem at all to falsify the DNS response. Why does an attacker want to do this? Because you are going to mybank.com, but you want that the victim gets back an IP address from not the real mybank.com website, but from a website that the attacker has built by himself. So this is why the attacker wants to use DNS spoofing. For example, if the attacker is on the internet, he can either be on an intermediate router or firewall, he can be in the man in the middle at layer 3, something like ARP spoofing or neighbor discovery spoofing. We had these issues, I think, 2 years ago with an BGP hijack. So there was this attack that the Route 53 DNS servers from Amazon AWS were hijacked through a BGP hijack, were redirected due to a BGP hijack. So this was not the problem of DNS, but the problem of BGP. However, within this attack, DNS spoofing was done because the attacker was now able to be in the middle of this DNS query answering process. Another attack is the cache poisoning. So the cache poisoning is that the attacker fools the recursive resolver to store some wrong values. Let me explain this DNS cache poisoning. So this DNS cache poisoning itself is like a 1-hour presentation along, so I will only show you this slide. If you're not interested, please don't look at it, fully fine. So the DNS cache poisoning works as follows. The attacker wants to fool the recursive resolver to store falsified RRs in its cache. How is he doing it? The attacker asks the recursive resolver for something, 01.mybank.com. And now what the attacker is doing, he guesses the source port and query ID from the recursive resolver as he asked this iterative DNS query to the authoritative name server. So because we know the resolver will exactly do this. He will send out a DNS query sourced from a source port with a query ID. And now what the attacker does, he guesses them, he spoofs like 600,000 or like 100,000 DNS responses, hoping that one of them made it to the answer to this recursive resolver. Now here's the trick. The attacker says something 01, that what he's asked himself, has not an A record directly, but it has a delegated name record to www.mybank.com. And in the additional section of this spoof DNS response, this concept is known as the glue records, because for name delegation, DNS thing, you will have this glue records. He's saying that, and by the way, www.bank.com with the high TTL is at this IPv4 address in this example. If he does not succeed within the very first try, he can try it with something 02, something 03, something 04. And so still, this is not security at all. And this attack really works. What's the problem here? The problem here is that this recursive resolver sending out its DNS queries to the authoritative DNS server with just the source port and this query ID as their identifiers. And the attacker is capable of spoofing 100,000 packets of them. This is what DNS cache poisoning is. So we have seen two examples, DNS spoofing, man in the middle, or DNS cache poisoning. What are the countermeasures for these attacks? The countermeasure is DNSSEC. So what is DNSSEC doing? DNSSEC is a technology that adds authenticity and integrity, but not confidentiality. That is, when you're using DNSSEC, nothing is encrypted. Everything is still in plain text. If you're using Wireshark, you can still see what the DNS query is about. But the operator of the authoritative DNS server has added DNS signatures to all of their zones, to every single host name within this zone. Consider it like a sibling record. So if I am the admin of this authoritative name server, I have a zone and I have a record like server 1 has the IPv4 address something something, then DNSSEC implements a sibling record which is called the RRSIG, the resource record signature for the A record. This is done via public-private key pair, as you probably know it. So this authoritative DNS server has generated a public and private key. The private key stays on the server, on the authoritative name server. The private key is used to sign the zone. The public key is sent to the parent zone, for example, .de for a German domain. And the parent zone signs the public key with their private key. So you have this chain of trust starting at the root zone. Now, when the recursive resolver asked the authoritative name server, he sends back the answer. So the recursive resolver can now verify the DNS signature. By doing this, this resolver verifies that the A record, for example, the IPv4 address is the same as it was sent by the authoritative name server. And he does know it because he can validate the signature with the public key. And he knows that the public key is the correct one because of this chain of trust, because this public key is the one where a parent zone has signed this public key. So by doing this, an attacker who does a DNS spoofing or an attacker who wants to try cache poisoning might still succeed with its attack, but it's immediately recognized because the recursive resolver knows that there's something wrong and it won't hand out this wrong answer to the client. This is what DNSSEC is about. So again, it's about authenticity and integrity. The recursive resolver wants to know that it got the right data. It's not about confidentiality. We are not encrypting anything. There are some more components for this DNSSEC. For example, we have the DNS key. This is another resource record within the DNS that holds the key for the zone. We have the concept of a key signing key and a zone signing key. I don't want to bore you here. We have the DS record. This is the one who is to the parent zone, and so on and so on. So for example, if you have an A record for the domain Weber DNS, for example, this A record holds an IPv4 address, and then you have a sibling record, the RRSIG for the A record, with some timestamps, with some key IDs, and then you have this public key signature. This is how it works. What tools can you use to troubleshoot DNSSEC? There is this tool called DNS-Wiz. Whether or not you're using DNSSEC, please consider using this tool. It's really cool. It's called dnswiz.net. When you add in a domain name in here, it will analyze this domain for DNSSEC, and it will print you this graphic. And with this graphic, I want to zoom in a little bit. Here you can see, for example, we are here at the root domain, the dot. We have the DE domain, and here at the bottom we have the Weber DNS, which is my domain. So we can see here, for example, the DE domain has this DS record. This is the sign. This is the verification of my public key. They have signed it, and this points to my public key that I'm using on my zone. My private key, which relates to this public key, now has signed all my different resource records. So within this tool, when you're implementing DNSSEC because you're the operator of an authoritative name server, or if you want to check if someone else has implemented this, please use this DNS-Wiz. If you're using dig, for example, to ask for a domain, you can look at the flags. There's a flag called AD. This AD flag reads authenticated data. So that is, I'm talking to a recursive resolver who has done the DNSSEC validation for me and tells me, well, we are using DNSSEC and it's validated. This is how this AD flag works. So for example, if I'm using dig Weber DNS.de, you can see I'm using a recursive resolver and I'm getting back the ID flag because this resolver has done the DNSSEC validation for me. If you... Yeah, I will come to that in a minute. Yeah. If you want to use dig, you can also use this plus DNSSEC option, and then you will see the resource signature itself. So if I'm doing here a dig weberdns.de plus DNSSEC, you can see that you have this resource signature. You won't ever look at this, but it's just if you want to troubleshoot it, you can use dig as always. Because, as Sake already said, when you're troubleshooting DNS, please don't use NSLookup, but use dig. Either on a Linux machine or even on a Windows machine, there are tools that you can use. Okay. Please be aware that the DNSSEC validation is normally done on resolvers, not on clients. That is, an attacker is still able to spoof the DNS responses if the attacker is between the resolver and the client, right? Yeah, just keep that in mind. If you want to check whether or not you are using a DNSSEC validating server, you can use a small website. It's called dnssecornot.com. Want to click at it? www.dnssec-or-not.com. And it makes a small test whether or not your server, the recursive DNS server you are using as of now, is doing DNSSEC validation. Caution. Attackers will sign their own zones as well. Coming back to this DNS exfiltration, the attacker has had this authoritative name server of attacker.biz or attack.biz, you remember? So an attacker might use DNSSEC for his own zone as well. So this is the same for an attacker who has my bad bank.site, and he has a TLS certificate on his web server. So because if the attacker is the owner of a server or is the owner of a host of a domain, he can also use DNSSEC. So just keep in mind that just because a zone is DNSSEC signed does not tell whether the zone is legitimate or not. It only tells you that when you are querying something on a bad zone, you just know that you have queried the right bad zone, but not whether or not this bad zone is legitimate or not. Okay, if you're interested in this DNSSEC stuff, I have a blog post series at about 20 blog posts where I dig into all those details, covering DNS and DNSSEC, how you can sign your zone with bind, how you can do troubleshooting, how you can roll over your keys, and so on. So it's on weberblog.net/DNS. There you will find the list. The last topic I want to point out today is dot and do. So I think this is what your question was a minute ago. Now with DNSSEC we have solved like this area. But still the client makes it recursive DNS query to the resolver, and here we have the last mile. So if the attacker is capable of doing a man-in-the-middle attack for doing DNS spoofing on this last mile, DNSSEC is not working anymore because the DNSSEC validation is done on the resolver, not on the client. Even more, the attacker can be a passive and he can simply listen on the shared medium. So if you're on a Wi-Fi network, on a guest Wi-Fi network, and you're using the same Wi-Fi key for all the attendees, for example, so you're not using WPA2 Enterprise, where everyone has its own session key, but you're using the same key for all, then an attacker might be able to eavesdrop, so he can listen to which DNS queries you are looking for. To solve this, we are using technologies called DOT or DO. DOT is DNS-over-TLS. DO is DNS-over-HTTPS. So this time, we are really encrypting, we are securing the DNS conversation. So we are using TLS. So here's how it works. Now, we're talking about confidentiality. So the first concept that has evolved was DNS-over-TLS. We have a well-known port, a registered TCP port for it, and this port is 853. DOT was meant to replace the normal stub resolver on your host operating system, as the stub resolver talks to the recursive resolver. So it was meant between the operating system and the resolver. For some reason, DOT did not really make it. So it was never really implemented by the operating systems and nobody cared. Who was not happy with the situation? It was the browser vendors or the browsers, for example, Chrome and Firefox. Because Chrome and Firefox, they had in their mind that they want to have a secure browser. They wanted to secure their users. They wanted that when you are on a public Wi-Fi or in a country where you are not allowed to do anything, or where it's not funny if someone else knows to which sites you are going to, they wanted to keep their users secure. So they have implemented something called DO, DNS-over-HTTPS. So this is TCP port equals 443, because it's a normal TLS session, it's a normal HTTPS session which uses TLS. In fact, it uses HTTP. So on the wire, we don't have this binary DNS queries that you would see on Wireshark, but you really have HTTP in the HTTP format wrapped in TLS. So this was developed for the browsers, basically for the browsers. But in the meantime, within the last, let's say, 5 years, this was also added on the operating systems. So for example, I think I have a screenshot here. When you're using Windows 11 and you're going to the DNS settings, you can add the DNS server, and then you can say DNS over HTTPS. Or within your Android, if you have an Android cell phone, you can enable DNS over HTTPS. So this is exactly what this is about. So this is kind of the history. In fact, dot won't be used ever, but do is used for real. Yes?
Very often I need to open my firewalls to the outside and so that I could talk to a malicious server on the outside.
Perfect question. This slide is for you. So the question is, doesn't this circumvent my internal DNS security? Yes, it does. So if you have a firewall rule allowing port 443 to the outside, and if your browser on your client's computer is using a DOH, public, reachable, unknown DOH server in the internet, and if you're allowing port 443 to the internet, you will have the problem that your DNS security that you're doing on the resolver, as I told you, and your DNS security on your firewall, as I told you, won't ever see a DNS query on UDP port 53 because the browser or the application itself uses DOH to some unknown server down in the internet. This is a real problem because all this DNS security that we have talked so far won't be used anymore. So what's the best practice? The best practice indeed is when we are looking at enterprise networks. I'm not talking about use a private person going to a public Wi-Fi. Please use DO. But when we talk about enterprise networks, in fact, the best practice as of now is either block DO on firewalls. So if you have this perimeter firewall, which does TLS interception, it will see that within your HTTPS stream, it's in fact a DNS-over-HTTPS query, and it will simply block it. And the client will fall back to its normal DNS behavior and will use the configured recursive resolvers within your local network. Or disable DO through group policies. So there are various ways how you can tell Firefox or Edge or Chrome through group policies within your enterprise network. Please don't use DO at all. A malware could still use it, correct, but then you should block it on the outgoing firewalls. Yeah. Or you offer DO on your resolver. So in fact, you could offer DO, DNS over HTTPS, on your own resolver and point your browser and point your operating system to your own DO resolver, because then you can still use your cool DNS security features on your own recursive resolver, and everyone is secured again. For example, if you have an enterprise company and you're operating a real big guest Wi-Fi with 10,000 of clients, and you want to secure your clients, you want that your clients are, you can use some DNS encryption, you could offer DO on your own resolver. Side note, I don't know, have you heard about DNS-over-EU? This is an EU initiative. If you want to use a public open resolver, please don't use Google public DNS 808. You could use, for example, the DNS-over-EU. So the domain is join DNS-over-EU. You can click here, set up your own DNS. So this DNS servers are co-funded by the European Union, and they have all these laws like GDPR and you name it. They have all this privacy stuff, but still those are anycast IP addresses in the internet that you can use as an open resolver if you want to. So you can scroll down a little bit and you have this protective resolution, set it up, and you can see here you have the IP addresses, IPv6 and legacy IP, and you also have these DNS over HTTPS or DNS over TLS servers. So here we don't use IP addresses, but host names. Why? Because the HTTPS server has a valid TLS certificate for this name rather than for an IP address. This is why we are using this one here. So yeah, please use this. If you want to play around with DO and DOT, you can use, again, you can use DIG. For example, DIG has a switch plus TLS or plus HTTPS, which uses then DNS over TLS or DNS over HTTPS. I prefer to use another tool. It's called DNS-DIAC. With DNS-DIAC, you have various tools. One of these tools is DNS-ping. DNS-ping is a cool troubleshooting tool because it pings a recursive resolver for DNS queries. So it's basically a per second, one query response communication. So if you want to troubleshoot the latency of DNS servers, or if you're doing an update on your DNS server and you want to be aware that not only the server is pingable through ICMP, but that it does respond to DNS queries, you can use, for example, this DNS ping. And DNS ping as well has this --TLS or --DO options, to use dot and do. Yes, please. Yeah, that's a good question. So the question is, when I'm using like this dig protective something for DNS. So the question is, how does dig, or how does my operating system know which IP address do I use for this domain? Good question. The answer is, it will use the normal DNS resolver on the operating system. Yeah, it kind of, yes, it does a fallback. In fact, there are some attacks out there because if you know that you're asking for this query, you can already point to another one, but then this other guy won't be able to have the valid HTTPS certificate and so on and so on. But yeah. Okay. If you want just to look at how these packets are on the wire, there's something called the ultimate PCAP. Who has ever used the ultimate PCAP? Okay, cool. Thanks for that. So I'm the author of this ultimate PCAP, and I recently added all those messages, like last week. So if you download the most recent version, you will find some do.doc do.h3, what I'm talking about. In a minute. Here I have a screenshot for Wireshark displaying some DO traffic. So everything you see here is that we have a destination port of 443. This SNI is protective something something, a client hello, but then we only have the server hello, change cipher spec, and then we have random looking encrypted data. So yeah, I mean, we are talking about confidentiality, so this is what we want in the end, that an attacker who passively sniffs on the network cannot see anything. This is how it works. I've tested those concepts through a Palo Alto Networks firewall without TLS interception. So what you see here is that for DNS-over-TLS, the TCP port 853, but the firewall itself only recognizes SSL traffic. Same for DOH. It's TCP traffic to port 443, but it's only SSL. Again, I'm not using TLS interception in this scenario, but this is just how the firewall sees it. There are some other variants. For example, there's DOQ, which is DNS over QUIC. This still uses the well-known, the registered port 853 on UDP. And there's a fourth one, it's called DNS over HTTP/3. This uses QUIC on port 443. So again, we have UDP on port 443, which is recognized here as QUIC base. As you can see, in all of those four variants, this firewall does not see a DNS. It does not recognize DNS at all, but just some encrypted stuff. Okay, let's come to an end. I have 1 minute left. Perfect. So if you want to make a photo, please make a photo of this one, because this tries to summarize everything we have done so far. So doing a rough summarization. We will have attackers or malwares on local computers that will use DNS to find their command and control servers. The attackers will use domain-generated algorithms to have repeatedly or to have easily many different host names. Or the malware, the phishing mail, will use a lookalike domain to fool the human brain. What can we do against this? We can implement feeds or block lists on the recursive resolver. Then we have an attacker who can DNS spoof or eavesdrop on your local network between your client, the stub resolver, and the recursive resolver. What can we do against this? We can implement DOE in order to have a secure channel between the client stub resolver or the client browser and the resolver. The attacker can use something like DNS exfiltration or DNS tunneling, or cache, just the first two, DNS exfiltration or DNS tunneling. He uses this recursive resolver. Again, what can we do against DNS exfiltration, DNS tunneling? We can use the deep query inspection in order to recognize this DNS tunneling events. And the attacker can do an attack called cache poisoning or DNS spoofing on the internet. What can we do against this? Well, the admins of the authoritative name servers have to sign their zones with DNSSEC, and we should implement DNSSEC validation. Okay, just clearing all my yellow stuff. So, long story short, the low-hanging fruit is definitely add DNSSEC validation on your recursive resolvers, because that's really easy and it works almost perfect. So please at least add DNS validation on your recursive resolvers. One more tip: when you're using, you want to use a secure DNS at your home network, please consider using the Pi-hole. Yeah, I think many of you might have heard of the Pi-hole. It's just a small software running on your local Raspberry Pi. With this, you will have this concept of DNS lists. So the Pi-hole will update lists with known malicious DNS names. It will not only block malware, but it also will block ads and tracking websites. You can activate DNS validation. It's literally one click and you're done. And you can use your own recursive resolver on the Raspberry Pi itself. So then you don't have this privacy issue anymore. This won't secure you against domain-generated algorithms. And it won't secure you against DNS exfiltration tunneling because it does not this deep query inspection. Okay, I have an installation guide on my blog as well. Just on my blog, you can Google like Pi-hole installation, you will find it. And there we are. Okay, this is just and it gives you some nice stats. So you can live look at your query log, you can whitelist or you have an allow list and a block list for your DNS queries and so on. Yeah, this is quite cool. Okay, I'm already a little over time. Just one more note. There are legitimate DNS tunnelings. So, yeah, kind of stupid. For example, McAfee, Spotify, or Apple are using some kind of DNS tunneling because they are querying their servers, which looks like DNS tunneling, but here it's kind of legitimate. Just that you have heard it. Okay, I'm out of time. What we have not talked about. We have not talked about DNS cookies, TSIG, EDNS0, DANE, it's used with DNSSEC. We have not talked about this text record in DNS for email, like SPF, DKIM, DMARC. We have not talked in detail about DOQ, DOH3, and so on and so on. So there are still way more topics, but I hope that you have gotten an overview of DNS security. Okay, coming to an end. If you like podcasts, I've started a security podcast. Unfortunately, it's only in German. Aber ich weiß, es sind einige deutsche Zuhörer hier auch. Also wer der deutschen Sprache mächtig ist und immer mal einen Security-Podcast hören möchte, würde mich freuen, den Security as a Podcast. Kleine Werbung in eigener Sache. And so we are finished for the session. Please rate it. And yeah, I have some stickers. Normally I'm talking about IPv6, this time not. However, I have still some IPv6 stickers and some stickers for the Ultimate PCAP and the Security as a Podcast. So in case you want some stickers, please get some. And yeah, please come to me if you have any questions later on. I will be here for the next days as always. And yeah, thanks for watching.